In the previous video, we talked about coordinates with respect to a basis. So, how to find out the coordinate of a vector with respect to a particular basis in a vector space. Now, this particular portion is to find out the transformation matrix. This transformation matrix will act as an operator and it will uh, convert the coordinates of the input vector to the map coordinates of the mapped vector in the new vector space. So, and the basic idea of this particular uh, finding of this particular transformation matrix is the definition of the coordinates. So let us just revisit the definition of the coordinates. The definition of the coordinates says that uh, it is the ordered pair or ordered list of the scalar multipliers which when multiplied by the basis vectors, corresponding basis vectors, then it will generate the vector again. So that is the basic understanding of coordinate system. Let us see, means you can see here. So the definition says something like this, that if you can write the vector x like this with respect to basis b, then the coordinate of x is equals to this one. So that is the definition. Now we are going to move to see this transformation matrix. Now what is our plan? Our plan is to is that initially, okay, initially we have a mapping phi which is going from v to w. We are mapping each element of v in w, and b is the basis of vector space v, and c is the basis of vector space w. Now any element, any vector in vector space v can be written as linear combination of uh, basis vectors, these basis vectors, and any vector in w can be represented as a linear combination of these vectors. Now let us see what happens. So since phi bj, so bj is this bj is an element of v, while all ci to cm are the elements of basis of w. So since phi bj is mapped from v to w, now the phi bj is an element of w. Now it should be able to, we should be able to write it as a linear combination of elements of c or the basis c. So that is what we are writing here, right? So what actually happens is that you can write any vector x, you can write any vector x, see here. So this is some vector x, so some vector x is like this, which can be written as linear combination of basis vectors, so bx cap, right? And why this? You can write like this. Why? Because every element of vector space v can be written as linear combination of basis vectors in b, and this particular b is the matrix containing the basis vectors of b as columns, right? So in that case bx cap is actually the linear combination of basis vectors in B, and the multipliers are going to get supplied from x cap, right? So phi x vector is equals to y vector. So y vector is the mapped vector in the space W, in the vector space W, and y hat is the coordinates of y vector with respect to basis C. So ultimately what we are trying to say is that whatever mapping, whatever linear mapping you take phi, when you take any vector x in this phi, it will ultimately change this vector to uh, the y vector. Now since it is a linear mapping, so you can express this bx hat like this, because it's a linear combination of basis vectors, and the correct multipliers are supplied from x hat. So these are the multipliers: x1 cap, x2 cap, xn cap, and these multipliers are supplied from x hat vector, or the coordinates of x vector with respect to basis B. So that is the definition of coordinates. So now this is the mapping. Now when we want to map this thing, since this mapping is a linear mapping, you can write like this, right? So once you can write like this, you can definitely will be able to write in that way, because you keep all the columns at one side and you can write it as a matrix multiplication. You can write always a linear combination of vectors as matrix multiplication. So that is what we have written in 1. Now similarly phi bj, this phi bj can also be written as this, because phi bj is nothing but some element or some vector in C, in vector space W. So every element of V will be mapped to W with respect to, or with the help of this mapping. Now since it is mapped to vector space W, this particular vector must have some coordinates with respect to the basis C, and whenever you have this, you can write it as a matrix multiplication. So you finally can write it like this, right? So ultimately, if you add up, or if you accumulate all the columns of a phi, you will get this, because you have phi b1, phi b1, phi bn like this, and then you are saying that this phi a phi has so many things, exactly like phi b1, phi bn. So something like that you are having here, and that's how you will be able to write that. You will be able to write this thing, that that you will be able to write like this, right? So that's what it is. Now from the above part, so one thing is that the same thing we can write like C a phi, and we have a, this is phi of bx cap, and this is equals to cy hat, right? And bx hat can be written like, can be written phi bx hat can be written like this way, and again this particular portion can be rewritten by, this way, or in fact this way. So ultimately what you get this equation. Now, interestingly, C is a basis. And now, since C is a basis, all the vectors in C must be linearly independent. All the vectors, all the column vectors of C must be linearly independent. And since it is all the vectors are linearly independent, you do not have any free variable, and you have a unique solution of this system of linear equations. Now, which essentially means that you can cancel this C out. You can cancel this C out, right? If you can cancel the C out, you get this thing. And now we have a method to transform x hat, that is the coordinate of a vector in the vector space V with respect to basis B, to and map it to vector space W, and we will find the coordinates with the help of A phi, the transformation matrix, into y hat, which is a coordinate with respect to basis C in vector space W. And that's all for this particular part as a proof. So there is one small question which we can see here. So we have certain phi b1, phi b2, phi b1, phi b2, phi b3. So we have to arrange these things in columns. So something like this you have to write, and then x hat here there should come. So you can see that if this is phi b, then a phi is like this. So this row is actually transformed to this column, right? This is a specific example of the transformation of a matrix A phi with respect to B and C. So that is the matrix for the rotation matrix. So you can check it from the mapping that we did with the linear in the previous part, part 8, so where we tried to find out what is the linear mapping, and we tried to know, and we proved in fact that rotation is a linear mapping, differentiation is a linear mapping. So you can see, you can take the matrices from that and try to identify what would be the transformation matrix for these operations. In the next part, we will see more of other type of some advanced topics. So as of now, we conclude this video.